While most of the world slept, a robotic telescope perched high in the Andes Mountains caught something that shouldn't exist. The Atlas system, designed to spot dangerous asteroids, had just detected an object moving through space at impossible speeds. The computer flagged it immediately. This wasn't normal. Within 6 hours, observatories in Hawaii and California confirmed what the Chilean telescope had found. The object was real. It was moving faster than anything from our solar system could move, and it was heading inward, toward the sun, toward us. They gave it a name that only astronomers could love, C/2025N1, later shortened to 3I/ATLAS. The I stands for interstellar. This was only the third confirmed visitor from another star system in human history. But there was something different about this one. Something that would soon have scientists around the world asking uncomfortable questions. The numbers told a story that made physicists double-check their calculations. This chunk of space rock, or ice, or whatever it was traveling at 130,000 miles per hour. To put that in perspective, that's about 170 times faster than a bullet. It could cross the entire United States in under 3 minutes. Nothing from our solar system moves that fast, unless something catastrophic has happened to it. But here's where it gets interesting. The object's path through space was almost too perfect. It would pass close enough to Earth for us to study it with our best telescopes, close enough to see details no one had ever seen on an interstellar object before, yet far enough away, about 270 million kilometers, that it posed no danger to our planet. If you were designing a trajectory for maximum scientific observation with minimum risk, you couldn't have planned it better. The first images were disappointing and thrilling at the same time. Through even our most powerful telescopes, 3I/ATLAS looked like a fuzzy dot with a faint tail. Classic comet behavior. Solar radiation was heating its surface, causing frozen materials to sublimate directly into gas. Nothing unusual there, except everything about this object was unusual. NASA scrambled its resources. The Hubble Space Telescope adjusted its schedule. The James Webb Space Telescope, our newest and most powerful eye in the sky, prepared to take a look. The European Space Agency called emergency meetings. This wasn't just another space rock. This was a messenger from another star system, carrying secrets from a place we could never visit. The initial observations raised more questions than they answered. The object seemed to be producing gas, like a normal comet. But the amount of gas didn't match its apparent size. The brightness wasn't quite right either. Too bright for something that small, unless it was made of unusually reflective material. Or unless the size estimates were wrong. Or unless scientists started whispering possibilities that would have been laughed at just a few years ago, because humanity had seen interstellar visitors before. And one of them, an object called Oumuamua, had behaved so strangely that serious scientists had asked a question that changed everything. What if it wasn't natural? As July turned to August, as more data poured in from telescopes around the world, that whispered question grew louder. 3I/ATLAS was about to challenge everything we thought we knew about what drifts between the stars, and some researchers were starting to wonder if drifts was even the right word. Something was coming. The question was, what exactly had we found? The email landed in newsrooms around the world on July 15, 2025. Dr. Avi Loeb, Harvard's controversial astrophysicist, had published his initial analysis of 3I/ATLAS. His conclusion? We shouldn't rule out artificial origin. The media explosion was instant and predictable. Alien probe heading for Earth, screamed the headlines. Twitter went insane. Cable news brought in experts who'd never studied astronomy. The real scientists cringed. But here's the thing. Loeb wasn't some crackpot. He was the former chair of Harvard's astronomy department, and he had reasons for his suspicions. It started with Oumuamua back in 2017. That first interstellar visitor had done something no space rock should do. After swinging around the sun, it accelerated. Not by much, about 100,000th of Earth's gravity, but enough to mess up every prediction. No jets of gas could explain it. No normal physics quite fit. Loeb had famously suggested it might be alien technology, perhaps a light sail pushed by solar radiation. The scientific community had mostly disagreed. They found natural explanations, even if those explanations required exotic physics. But the seed was planted. What if some interstellar objects weren't natural? What if we were seeing alien probes mixed in with the cosmic debris? Now 3I/ATLAS was displaying its own peculiarities. The speed was one thing, the trajectory was another. But what really caught Loeb's attention was the chemistry. Early spectroscopic data from the James Webb Space Telescope showed something bizarre. Way too much carbon dioxide, not enough water. The ratio was 8:1. Every comet we'd ever studied was mostly water ice. This thing was breathing out CO2 like some kind of cosmic exhaust system. When nature surprises us this much, Loeb wrote, we must at least consider non-natural explanations. The counter-arguments came fast. Dr. Karen Meach from the University of Hawaii, who'd led the Oumuamua studies, pointed out that we'd only seen 3 interstellar objects. 3 data points don't make a pattern. We didn't know what was normal for objects from other star systems. Maybe they all had weird chemistry. Maybe they all moved strangely. But the public had already made up its mind. Online forums dissected every image. Amateur astronomers tried to spot it through backyard telescopes. The hashtag Atlas Alien trended for weeks. Everyone had a theory. It was a probe. It was a weapon. It was a derelict spaceship. It was deliberately aimed at Earth. The timing didn't help calm anyone down. Just a month earlier, Congress had held hearings on UAPs now, with military officials testifying about objects that defied explanation. The mood was already primed for alien revelations. 3I/ATLAS felt like the universe's answer to our questions. Professional astronomers found themselves in an awkward position. They couldn't completely dismiss the artificial hypothesis without data. That's not how science works. But they also couldn't endorse it without evidence. So they did what scientists do. They observed, they measured, they argued. The debate revealed something profound about how we think about aliens. We expect them to announce themselves clearly. Giant ships, radio signals, something obvious. But what if alien technology was subtle? What if it was designed to look natural? What if we'd been seeing it all along and dismissing it as weird space rocks? By early August, every major telescope on Earth was tracking 3I/ATLAS. The verdict from most scientists, probably natural, but keep watching. The verdict from Loeb, probably natural, but we can't be sure. The verdict from the public, aliens, definitely aliens. Let's talk about speed. Not highway speed, not airplane speed. We're talking about 130,000 miles per hour. That number should make you uncomfortable. Here's why. In our solar system, things move in predictable ways. Earth orbits the Sun at about 67,000 miles per hour. Comets at their fastest might hit 100,000. But 3I/ATLAS was cruising at 130,000. And it wasn't even trying. This was its natural velocity, the speed it maintained while coasting through interstellar space. That kind of momentum doesn't come from our neighborhood. To achieve that speed, you need violence, cosmic violence. Maybe a close encounter with a giant planet that slingshots you out of your home system. Maybe a stellar explosion. Maybe a 3-body interaction, where multiple stars play gravitational ping-pong with smaller objects. Or maybe, and this is where it gets interesting, maybe you need engines. Dr. Konstantin Batygin at Caltech ran the numbers. For a natural object to reach 3I/ATLAS's, velocity would require a perfect storm of gravitational assists. Not impossible, but extremely rare. We're talking about winning the cosmic lottery, he said in an interview. This thing got kicked hard by something. But here's the detail that kept scientists up at night: the trajectory precision. 3I/ATLAS wasn't just fast, it was aimed. Its path would bring it within 1.8 astronomical units of Earth, close enough for detailed study, but far enough to pose no danger. It would pass Mars at an even closer distance. It would swing by the Sun at the perfect angle for gravitational focusing. If you were programming a reconnaissance drone, this is exactly the path you'd choose. The speed also meant something else. Whatever star system had launched this object, intentionally or otherwise, had done so when our solar system was in a completely different part of the galaxy. The calculation required to hit such a precise trajectory from such a distance was mind-boggling. Unless it was just cosmic coincidence. The universe is full of those, right? Compare this to bullets. A rifle bullet travels at about 1,700 miles per hour. 3I/ATLAS moves 76 times faster. It could circle Earth's equator in 12 minutes. It could reach the moon in 2 hours. These aren't speeds we associate with random space debris. These are speeds that suggest purpose, urgency, or at minimum, an origin story involving tremendous forces. The physics community split into camps. The naturalists argued that high-speed objects were probably common in interstellar space. We just hadn't detected them before. The space between stars might be full of hypervelocity fragments from ancient stellar collisions. 3I/ATLAS was just our first good look at this population. The skeptics, Loeb among them, pointed out that speed plus precision plus unusual chemistry was a lot of coincidences. In science, when coincidences pile up, you start looking for underlying causes. Maybe the cause was natural, but exotic. Or maybe it wasn't natural at all. NASA's trajectory analysts confirmed something else unsettling. 3I/ATLAS's path showed no signs of course correction from passing stars. Over millions of years of travel, gravitational perturbations should have altered its trajectory slightly, but the path was too clean, too direct, as if it had been traveling for a much shorter time than its speed suggested, or as if something had been correcting its course. By late August, the speed of 3I/ATLAS had become more than just a number. It had become a challenge to our understanding of what moves between the stars and why. Every mile per hour above normal was another question mark. Another reason to wonder what exactly was racing toward us. The universe, it seems, has been trying to tell us something. 3 times in less than a decade, interstellar objects have visited our solar system, each one stranger than the last. Together, they paint a picture that's either coincidence or communication. Let's review our cosmic guests. First came Oumuamua in 2017. The Scout. Discovered as it was already leaving, this object defied every expectation. Shaped like a cigar or a pancake, scientists still argue about which. It tumbled through space like a thrown stick. No visible tail, no comet-like activity, just a dark, reddish object reflecting sunlight in ways that didn't quite make sense. Then it accelerated. As Oumuamua left our solar system, it sped up, not from any visible jets of gas, not from any process we could detect. It just pushed harder away from the sun than gravity alone could explain. The explanations ranged from exotic, hydrogen ice we couldn't see, to extreme, Loeb's light sail hypothesis. We still don't know what caused it. 2 years later, 2I/Borisov arrived, the normal one. Finally, an interstellar visitor that behaved exactly like our models predicted. It had a proper tail, released gas and dust like a textbook comet, and followed a trajectory that made perfect gravitational sense. Borisov was so normal it was almost disappointing. Except for one thing. Its carbon monoxide levels were off the charts. Way more than any comet from our solar system. Different chemistry meant different origins, but at least it acted like a comet should. Scientists breathed a sigh of relief. See? Most interstellar objects are normal. Oumuamua was just weird. We'd built theories around Borisov. Interstellar objects were just regular comets and asteroids from other star systems. Nothing special. Nothing artificial. Case closed. Then 3I/ATLAS showed up and ruined everything. It was faster than both previous visitors. Its carbon dioxide emissions dwarfed anything we'd seen. The gas cloud around it extended farther than Earth's orbit. It was too bright for its size, or too big for its brightness. We couldn't tell which. Every measurement seemed designed to confuse our instruments and challenge our assumptions. 3 visitors. 3 completely different chemical signatures. 3 different behaviors. It was like the universe was sending us samples from 3 different laboratories, each one following different rules of physics. Or maybe, and this is where even skeptical scientists started to wonder, maybe they weren't random samples at all. Dr. Sean Raymond from the Bordeaux Astrophysical Laboratory pointed out an uncomfortable fact. The odds of detecting 3 interstellar objects in such quick succession were astronomically low. Either we'd gotten incredibly lucky, or something had changed. Maybe our detection technology had reached a threshold. Or maybe the objects themselves had become more frequent. Or maybe they'd always been there, and we'd just started looking in the right way. The pattern, if it was a pattern, suggested escalation. Oumuamua, weird shape, weird acceleration. Borisov, normal behavior, weird chemistry. 3I/ATLAS, weird everything. Each visitor pushed the boundaries of what we thought possible a little further. Each one forced us to expand our definitions and revise our theories. Some researchers started calling it the interstellar zoo hypothesis. Maybe we were seeing representatives from different cosmic environments, different star systems producing different kinds of objects, like different countries producing different cars. Natural variation explaining all the weirdness. But others wondered about a different kind of zoo. The kind where the animals aren't random. The kind where someone chooses what to show you and when. 3 visitors in 8 years after billions of years of nothing. What were the odds? Here's the number that let everyone sleep at night. 1.8 astronomical units. That's how close 3I/ATLAS would come to Earth at its nearest approach in December 2025. Let's put that in perspective so you can properly appreciate why scientists were both relieved and frustrated. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So 1.8 astronomical units means 3I/ATLAS would pass us at roughly 167 million miles. That's farther than the Sun. It's like standing in New York and worrying about a bullet fired in Tokyo. Even if this thing was aimed at us, even if it could somehow change course, it would miss by a margin so large that calling it safe is an understatement. Mars, by comparison, comes within 35 million miles of Earth at its closest approach. We regularly send spacecraft there. The Moon is only 238,000 miles away. 3I/ATLAS would pass us at 700 times the Moon's distance. If Earth was a basketball, 3I/ATLAS would miss us by about 3 football fields. We were absolutely, completely, utterly safe, which frustrated the hell out of scientists. See, 1.8 astronomical units is perfect for safety, but terrible for detail. Our best telescopes can see galaxies billions of light years away, but those galaxies are enormous. 3I/ATLAS was probably a few miles across at most. At 167 million miles, even Hubble would struggle to see it as anything more than a fuzzy dot. We could detect its gases, measure its spectrum, track its movement, but we couldn't see its actual shape or surface features. Dr. Michelle Bannister from the University of Canterbury called it the cosmic tease distance. Close enough to know something interesting was happening. Too far to understand exactly what. Like trying to identify a person from across a football stadium using binoculars. You can see they're human, see they're wearing clothes, maybe even tell their hair color. But their face, their expression, forget it. The safety margin did offer one advantage: time. Objects passing closer to Earth zip by in days or weeks. But 3I/ATLAS's trajectory meant we'd have months to observe it. From July through March, it would remain within range of our instruments. That's a long observation window for something moving at 130,000 miles per hour. NASA's Planetary Defense Coordination Office ran the numbers repeatedly. No possible gravitational perturbation could bring 3I/ATLAS closer to Earth. Even if it broke apart, the fragments would follow essentially the same path. Even if it was somehow powered and tried to change course, the energy required to close a 167 million mile gap would be impossible to generate. But here's where the conspiracy theorists had a field day. The distance was too perfect. Close enough for a probe to scan Earth in detail, but far enough to avoid our defenses. Close enough to be seen, but far enough to remain mysterious. If you were an alien civilization sending a reconnaissance mission, this is exactly the distance you'd choose. The scientists had a different interpretation. This distance was perfect because we could only detect objects this bright at this distance. There might be hundreds of interstellar objects passing closer or farther that we simply couldn't see. We were suffering from observation bias, seeing only the objects that happened to pass through our detection sweet spot. Either way, 1.8 astronomical units meant one thing for certain: we were safe. Whether 3I/ATLAS was a comet, an alien probe, or something else entirely, it would pass Earth at a respectful distance. We could watch, wonder, and worry, but we couldn't touch it. And it couldn't touch us. July 21st, 2025. The Hubble Space Telescope, humanity's most famous eye in the sky, turned toward 3I/ATLAS. After 20 days of anticipation, we were about to get our first clear look at our interstellar visitor. The image that came back would launch 1,000 arguments. It was beautiful and disappointing in equal measure. Against the star-studded background of space, 3I/ATLAS appeared as a bright central point surrounded by a diffuse, teardrop-shaped cloud. The coma, that fuzzy atmosphere of gas and dust, stretched asymmetrically away from the sun's direction. Classic comet behavior. Case closed, right? Not quite. The first problem was the brightness. Based on its distance and assumed composition, 3I/ATLAS should have been dimmer. Either it was larger than expected, more reflective than normal comets, or something about it was generating extra light. None of these options fit neatly with conventional comet models. The second problem was what Hubble couldn't see. The nucleus, the solid core of the object, remained completely unresolved. Even with Hubble's incredible resolution, 3I/ATLAS's heart was just a point of light. The upper limit on its size was about 3.5 miles across. That's smaller than Manhattan. Yet this tiny object was generating a coma visible from 400 million miles away. Dr. David Jewett at UCLA, who'd studied countless comets through Hubble, found something odd in the images. The dust distribution wasn't uniform. There were subtle variations in the coma's density that suggested active regions on the nucleus. Specific spots were venting material more vigorously than others. This wasn't unusual by itself, but the pattern didn't match typical comet behavior. Normal comets show jets of material streaming from sun-facing areas where ice sublimates most quickly. But 3I/ATLAS's emission pattern was almost too organized. The jets appeared to be coming from specific points that remained consistent across multiple observations, as if there were vents or ports releasing material in a controlled manner rather than random weak spots in an icy surface. The color was wrong too. Hubble's filters revealed that 3I/ATLAS was slightly redder than typical comets. Not dramatically so, but enough to notice. Red usually means organic compounds or certain minerals that have been processed by radiation. For an object that had spent millions of years in interstellar space, this made sense. But it also meant the surface had been altered, transformed into something we'd never seen before. Then there was the tail situation, or rather, the lack of one. Hubble's initial images showed the coma, but no clear tail extending away from the sun. Every comet at this distance should show at least a faint tail as solar wind pushes dust and gas away from the nucleus. 3. I/ATLAS seemed to be holding its material close, defying the solar wind that should have been sculpting it into the classic comet shape. Hubble took multiple exposures over several hours, tracking 3 I/ATLAS against the background stars. In these stacked images, stars appeared as bright streaks while the comet remained fixed at center. The technique revealed fainter details in the coma structure. There were shells of material, like tree rings made of gas and dust, suggesting periodic releases rather than steady emission. The Hubble team released the images to the public with careful scientific captions, but the internet had its own interpretations. Enhanced, filtered, and processed versions flooded social media. People saw shapes in the coma, structures in the dust. Some claimed they could see the actual nucleus, though astronomers confirmed this was impossible. What Hubble showed us was a familiar stranger. Something that looked like a comet, but didn't quite act like one. Something obeying most of the rules, but breaking just enough to keep us guessing. The telescope would continue monitoring 3 I/ATLAS for months, but this first look had set the tone. We were dealing with something that wouldn't fit neatly into our categories. August 6, 2025. The James Webb Space Telescope aimed its golden mirrors at 3 I/ATLAS and found something that made astronomers question their instruments. The chemical signature coming from our visitor was unlike anything in the comet catalogue. It was as if someone had rewritten the recipe for what comets should be made of. The headline discovery: carbon dioxide everywhere. Not just a little CO2 mixed with water vapor like normal comets. This was CO2 domination. The ratio was 8:1, 8 times more carbon dioxide than water. To understand how weird this is, imagine ordering a coffee and getting 8 parts milk to 1 part coffee. It's not coffee anymore. It's something else entirely. Dr. Stephanie Milam at NASA's Goddard Space Flight Center led the analysis. She'd studied dozens of comets with Webb, but this spectrum made her team triple-check their calibration. "We thought something was wrong with our instruments," she said later. "Comets are supposed to be dirty snowballs, emphasis on the snow. This was more like a dirty, dry ice ball." Water is the main ingredient in every comet we've ever studied up close. It makes up 80 to 90% of most comet ice. Carbon dioxide usually accounts for maybe 10 to 15%. But 3 I/ATLAS had flipped this completely backward. It was venting CO2 like a shaken soda bottle while barely releasing any water at all. The temperature made it even stranger. At 3 I/ATLAS's distance from the Sun, carbon dioxide should be sublimating, turning directly from ice to gas. But water ice should be doing the same thing, just at a slightly lower rate. The fact that we saw lots of CO2 but barely any water suggested something was actively preventing the water from escaping. 3 theories emerged, each stranger than the last. Theory 1. 3 I/ATLAS formed in a region of space where carbon dioxide was abundant, but water was rare. Maybe near a CO2 snowline in its original star system. This would make it a sample from an alien environment completely different from our solar system's chemistry. Theory 2. The surface was covered in some kind of organic crust that trapped water ice but let CO2 escape through cracks, like a sealed jar with a few holes poked in the lid. The water was there, but couldn't get out. Theory 3. And this is where even conservative scientists started raising eyebrows. The CO2 wasn't from ice at all. Maybe it was being produced by some process we didn't understand. Chemical reactions, biological activity, or even mechanical systems releasing stored gas. The Webb data showed something else peculiar. The CO2 emissions were remarkably pure. Usually, when comets release gas, it comes with a cocktail of other molecules: ammonia, methane, carbon monoxide, various organic compounds. But 3 I/ATLAS's emissions were almost clinical in their simplicity. CO2 and not much else. Dr. Martin Cordiner from Catholic University pointed out that such pure emissions were hard to explain naturally. It's like finding distilled water in nature. Possible, but it makes you wonder if something has processed or refined it. The spectroscopic data also revealed absorption features that didn't match any known comet minerals. There were hints of complex carbon chains, possibly organic polymers, that had been transformed by millions of years of cosmic radiation. Or possibly something else. The spectra had gaps where certain wavelengths were being absorbed by unknown compounds. By mid-August, chemists around the world were proposing increasingly exotic explanations. Some suggested 3I/ATLAS might be a fragment of a carbon planet, a theoretical type of world made mostly of carbon compounds, instead of silicon and oxygen like Earth. Others wondered if we were seeing the result of industrial processes, the cosmic equivalent of exhaust or waste products. The chemistry broke the rules, and in science, when something breaks the rules, it's either showing you new rules or showing you that the game is different than you thought. The Neowise Space Telescope made the discovery that broke physicists' brains. Between August 8th and 12th, it mapped the full extent of 3I/ATLAS's carbon dioxide cloud. The results were impossible. The CO2 coma stretched for 348,000 kilometers, nearly 250,000 miles. That's almost the distance from Earth to the Moon. Let's think about what this means. The solid nucleus of 3I/ATLAS was, at most, 3.5 miles across. Yet it was maintaining a gas cloud 70,000 times its own diameter. It's like a golf ball creating a fog bank the size of a city. The physics didn't add up. Dr. Amy Mainzer, Neowise's principal investigator, called it the most extended coma relative to nucleus size we've ever observed. That was the polite, scientific way of saying it shouldn't exist. Here's the problem. Gas expands in space. Without atmosphere to contain it, molecules fly apart at hundreds of meters per second. For a coma to stay that large and dense, the nucleus would need to be pumping out tremendous amounts of CO2 continuously. But a 3.5-mile wide chunk of ice simply didn't have enough surface area to generate that much gas through normal sublimation. The calculations were unforgiving. To maintain a coma that size, 3I/ATLAS would need to be losing about a ton of material every second. At that rate, an object its size would completely evaporate in months. Yet it had been active since at least July, showing no signs of shrinking. Where was all this gas coming from? 4 explanations competed for acceptance, each with its own problems. Explanation 1. 3. I/ATLAS was actually much larger than we thought. Maybe our size estimates were wrong by a factor of 10. But that would make it the brightest comet ever recorded at this distance, which didn't match other observations. Explanation 2. The nucleus was fragmenting, breaking into thousands of pieces that were all outgassing independently. This would create a distributed source of CO2 that could maintain the huge coma. But fragmentation should produce visible changes in brightness and structure that we weren't seeing. Explanation 3. Something about interstellar space had changed 3I/ATLAS's ice into a super volatile form that sublimated far more efficiently than normal. Millions of years of cosmic ray bombardment might have created a kind of freeze-dried honeycomb structure that released gas explosively when heated. Theoretically possible, but never observed. Explanation 4, and you knew this was coming. The cloud wasn't entirely natural. If something was actively releasing CO2 from internal storage, or producing it through chemical or mechanical processes, it could maintain a coma far larger than passive sublimation would allow. The cloud's structure offered more puzzles. Instead of the smooth spherical distribution you'd expect from simple outgassing, Neowise detected shells and layers within the coma, concentric rings of varying density, like ripples in a pond. These suggested periodic releases of material rather than steady emission. Something was controlling the outgassing, naturally or otherwise. The expansion velocity was wrong too. The CO2 molecules were moving outward faster than thermal velocity alone could explain. Something was accelerating them. Solar radiation pressure could do this, but not to the degree observed. Electric fields from charged particles might contribute, but the effect was too strong. Dr. Quanji Ye from the University of Maryland ran hydrodynamic simulations trying to reproduce the observed cloud. Every model failed. Either the coma was too big, too fast, or too structured. It's like trying to model a hurricane and getting a square cloud, he said. The physics just doesn't want to do what we're seeing. By late August, the cloud around 3I/ATLAS had become the single biggest mystery about our visitor. It was too big to exist, yet there it was, photographed by multiple telescopes, measured by different instruments, impossible to deny. Something was happening around 3I/ATLAS that we didn't understand. The question was whether that something was exotic physics or exotic technology. Something was wrong with how 3I/ATLAS moved through space. Not its trajectory. That followed the laws of gravity perfectly. But its rotation, or lack thereof, defied everything we knew about how small bodies behave in the solar system. Every asteroid and comet we've ever studied tumbles. It's basic physics. Collisions over millions of years set them spinning chaotically. Outgassing jets push them like tiny rockets, changing their rotation. Solar heating creates torque. They should tumble like dice thrown across a cosmic table. 3. I/ATLAS didn't tumble. It glided through space with the stability of a gyroscope. Dr. Matthew Knight at the University of Maryland led the photometry campaign, measuring the object's brightness every few hours for weeks. The data should have shown regular variations as different faces rotated toward Earth. Bright, dim, like watching a spinning mirror ball. Instead, the brightness stayed constant, flat line steady. 3 possibilities, each with problems. 1. 3I/ATLAS was spinning perfectly pole-on relative to Earth. We were looking straight down its rotation axis, so its cross-section never changed from our perspective. The odds of this alignment? Astronomically low, like flipping a coin and having it land on its edge. 2. The object was nearly spherical with uniform surface properties. No bright spots, no dark patches, no irregular features. But we'd seen the asymmetric coma. We knew material was venting from specific locations. A perfectly uniform sphere doesn't create jets and shells of gas. 3. It wasn't rotating at all. Something was keeping it oriented in a specific direction. That third option should have been impossible. Everything in space rotates. Conservation of angular momentum demands it. Unless something was actively controlling its orientation, like reaction wheels or gyroscopes or thrusters, the kind of attitude control systems we put on spacecraft. Then there was the tail problem, or rather the missing tail problem. By August, 3I/ATLAS had been actively outgassing for over a month. Solar wind should have been pushing that material into a classic comet tail stretching millions of miles behind it. Every comet at this distance shows a tail. It's not optional, it's physics. But 3I/ATLAS kept its gas close, like it was holding its breath. The coma stayed roughly spherical, maybe a bit elongated toward the sun, but no dramatic tail streaming behind it. When Gemini South finally detected a faint tail structure on August 27th, it was subtle to the point of invisibility. You had to process the images heavily just to see it. Dr. Meach called it pathologically shy for a comet. The tail was there, technically, but orders of magnitude fainter than it should have been, as if the dust particles were too heavy to be pushed by radiation pressure, or as if something was preventing them from escaping the coma's influence. The activity patterns made even less sense. Active comets show variations in their gas production. They breathe. More gas when the sun heats active regions, less when those regions rotate into shadow. It creates a rhythm in the data, a heartbeat of sublimation. 3I/ATLAS's gas production was metronomic in its consistency. Same rate, day after day, regardless of solar angle or distance. The CO2 just kept coming at a steady pace that ignored the changing solar environment. It was like watching a machine operate rather than a natural process respond to heating. The strangest behavior emerged from radio observations. Several teams pointed radio telescopes at 3I/ATLAS, looking for signals that might indicate electrical activity or unusual chemistry. They found silence. Not normal silence, the kind of silence that meant the object was absorbing radio waves rather than reflecting them. Objects in space should reflect some radio energy, especially if they're surrounded by ionized gas. 3I/ATLAS seemed to be eating radio waves, absorbing them without reflection or emission. It was radio dark in a way that didn't match its optical brightness. By September, the behavioral anomalies had piled up like evidence in a court case. No tumbling, no proper tail, steady outgassing, radio absorption. Each behavior had a possible natural explanation, but together they painted a picture of something that wasn't quite following the comet playbook. Never in history had humanity pointed so much hardware at such a small target. By late August 2025, 3I/ATLAS had become the most observed object in the solar system after the Sun itself. Every major space agency, every significant observatory, and thousands of amateur astronomers had joined what NASA called the most coordinated astronomical campaign ever attempted. The numbers were staggering. 16 space telescopes, 43 major ground observatories, over 200 university instruments, an estimated 10,000 amateur telescopes, all focused on a chunk of ice and rock, no bigger than a small mountain. NASA's response team worked out of Goddard Space Flight Center, coordinating observations like air traffic control. Hubble got priority windows. James Webb took infrared duty. TESS looked for brightness variations. Swift caught ultraviolet emissions. Each telescope had its specialty, its piece of the puzzle. The European Space Agency ran parallel operations from their center in Germany. Their fleet included Solar Orbiter, which could observe from a different angle than Earth-based telescopes. The European Southern Observatory dedicated multiple nights of very large telescope time, cancelling other programs to focus on 3I/ATLAS. But here's what made this campaign unique: the data sharing. Usually, astronomical data gets hoarded. Researchers sit on observations for months or years, publishing papers, claiming discoveries. Not this time. Every major institution agreed to immediate data release. Raw images, spectra, measurements, everything went public within 24 hours. Dr. Kelly Fast, NASA's Near-Earth Object Observations Program Manager, called it astronomy without borders. A graduate student in India could analyze Hubble data. An amateur in Brazil could compare their observations with professional telescopes. The entire planet became one giant research team. The coordination required was insane. 3I/ATLAS moved across the sky at about 3 degrees per day. That meant it crossed from one constellation to another every week. Telescopes had to hand off observations like relay runners passing a baton. When it set for Hawaii, Chile picked it up. When Europe lost it, Australia took over. Time allocation committees, the gatekeepers of telescope access, threw out their rulebooks. Normal proposals took months of review. 3I/ATLAS got same-day approval. One team calculated that the combined telescope time dedicated to this single object was worth about $100 million. China's Fast Radio Telescope, the world's largest single dish, listened for any radio emissions. The Very Large Array in New Mexico searched for magnetic field interactions. The Atacama Large Millimeter Array in Chile looked for molecular emissions invisible to optical telescopes. If 3I/ATLAS was broadcasting anything, we'd hear it. Amateur astronomers organized through online forums, creating a parallel observation network. They couldn't match professional telescope resolution, but they had numbers. Someone, somewhere, was always watching 3I/ATLAS. They caught brightening events that lasted minutes. They tracked subtle color changes. They provided the continuous coverage that even professional observatories couldn't maintain. The data pipeline strained under the load. The Minor Planet Center, which normally processed a few thousand observations per day, suddenly dealt with hundreds of thousands. Cloud storage systems that usually handled gigabytes were moving terabytes. Internet astronomy forums crashed repeatedly from traffic. But the elephant in the room was approaching fast: solar conjunction. On September 29th, 3I/ATLAS would disappear behind the sun from Earth's perspective. For 7 weeks, our entire observation network would be blind. The visitor would pass through perihelion, its closest approach to the sun, completely unobserved. NASA had one card to play: Mars. The red planet would be positioned to see 3I/ATLAS during part of the conjunction period. The Mars Reconnaissance Orbiter and other Mars missions were reprogrammed for opportunity observations. It wasn't ideal. These spacecraft were designed to study Mars, not distant comets, but it was better than nothing. The September push intensified. Every clear night, every available instrument, every possible observation. We had weeks to gather enough data to last through the blackout. The global watch had become a race against celestial mechanics. And everyone involved knew the same thing. When 3I/ATLAS emerged from behind the sun in November, it might be changed, or gone, or revealed as something we never expected. Let's say it's artificial, not suggesting it is, but let's explore what that would mean. If 3I/ATLAS was technology rather than ice and rock, what would we be looking at? The engineering requirements alone would redefine our understanding of what's possible. First, the journey. If 3I/ATLAS was a probe, it had been traveling for millions of years, maybe billions. Any technology that could survive that long in interstellar space would be beyond our current capabilities by orders of magnitude. Cosmic rays destroy electronics. Micrometeorite impacts erode surfaces. Extreme cold makes materials brittle. Yet here was something still active, still functioning. The power source would need to be extraordinary. Solar panels wouldn't work in interstellar space, too dark. Nuclear batteries like those on Voyager last decades, not millennia. Fusion reactors are still science fiction for us. Whatever was powering the CO2 emissions and maintaining that enormous coma would need to be something we haven't invented yet. Dr. Jason Wright at Penn State, who studies technosignatures, outlined what we should look for. Artificial objects should show non-random patterns in their emissions, structured data in their radio signals, materials or isotope ratios that don't occur naturally, behaviors that serve purposes rather than following physics. The disguise problem was trickier. If an alien probe wanted to avoid detection, mimicking a comet would be brilliant. Comets are common, temporary, and expected to behave strangely. The outgassing would provide natural camouflage for any emissions. The coma would hide the actual structure. It would be like hiding a submarine by making it look like a whale. But why announce yourself with excessive CO2? Why maintain such a huge coma that it draws attention? Unless drawing attention was the point, maybe it wasn't trying to hide. Maybe it was trying to be noticed by civilizations advanced enough to recognize the anomalies. The trajectory suggested intention. 3I/ATLAS would pass through the habitable zone of our solar system, close enough to observe Earth in detail, but far enough to avoid any defensive response. It would sample our solar wind, map our magnetic fields, and catalogue our planets. The perfect survey mission. SETI researchers had protocols for this scenario. The Rio scale, like the Richter scale for earthquakes, measured the significance of potential contact, 3I/ATLAS, currently rated a 2 or 3. Interesting, but unconfirmed. If we found structured signals or clearly artificial materials, it would jump to 8 or 9, civilization-changing discovery. But the probe hypothesis had problems, big ones. Why use such primitive propulsion? Any civilization that could build interstellar probes should have better ways to move than passive drifting. Why the specific chemistry? CO2 isn't particularly useful for anything we can imagine. Why remain silent? If you traveled millions of years to visit another star system, wouldn't you try to communicate? Dr. Loeb had answers for these objections. Maybe it was damaged, running on backup systems. Maybe the CO2 was waste products from internal processes. Maybe it was communicating in ways we couldn't detect. Or maybe it was a derelict, technology that had outlived its creators, still following ancient programming. The reference point was always Oumuamua. That first visitor had shown acceleration without visible propulsion. If one interstellar object could violate our expectations, why not 2 or 3? Maybe artificial probes were common and we just started noticing them. The key test would be December. When 3I/ATLAS emerged from solar conjunction, it should be changed. The intense solar heating at perihelion should alter its activity, possibly trigger fragmentation, definitely affect its outgassing rate. If it emerged unchanged, still producing the same steady CO2, still maintaining that impossible coma, the artificial hypothesis would gain credibility. Nobody wanted to say aliens out loud in scientific papers, but in conference rooms and coffee breaks, researchers were doing the math. The galaxy was 13 billion years old. Humanity had achieved spaceflight in less than a century. If even a tiny fraction of star systems developed technology, the galaxy should be full of probes. Maybe we just found one. Where did 3I/ATLAS come from? The question sounds simple until you realize you're trying to trace an object's path backward through millions of years of gravitational chaos. It's like trying to figure out where a leaf in a river started by watching it float past. Except the river is the galaxy, and the leaf has been traveling since before humans existed. Dr. Corinne Baylor-Jones at the Max Planck Institute led the backtracking effort. Using data from the Gaia Space Telescope, which had mapped the positions and velocities of over 1 billion stars, his team ran 3I/ATLAS's trajectory backward through time. The computational requirements were staggering, modeling gravitational interactions with thousands of stars across millions of years. The results pointed to something unexpected: the galactic thick disk. Our galaxy has layers, like a cosmic sandwich. The thin disk, where our sun lives, contains younger stars rich in heavy elements. The thick disk above and below it contains older stars, formed when the galaxy was maybe half its current age. These stars have different chemistry, different orbits, different histories. 3I/ATLAS's velocity and direction suggested it came from the thick disk population. That meant it was old, really old, possibly ejected from its home system 5 to 10 billion years ago, when the universe looked very different than today. But here's where it gets weird. The trajectory was too clean. Over millions of years, passing stars should have gravitationally nudged 3I/ATLAS countless times. Each encounter would alter its path slightly, creating a chaotic history impossible to reconstruct. But the models suggested 3I/ATLAS had experienced fewer perturbations than expected, as if it had been traveling for a shorter time than its speed suggested, or as if something had been correcting its course. The specific stars along its path raised eyebrows. HD 164595, a sun-like star 94 light-years away, sat almost perfectly along 3I/ATLAS's trajectory. The alignment was so precise that some researchers wondered if it was coincidental. If 3I/ATLAS had been launched from that system about 1 million years ago, the travel time and direction would match perfectly. HD 164595 had a history. In 2016, Russian astronomers detected a strong radio signal from its direction. The signal was never confirmed, probably terrestrial interference, but it had put the star on SETI watch lists. Now, an interstellar object was arriving from exactly that direction. Coincidence? Probably, but the kind that made scientists uncomfortable. The chemical clues supported an old origin. The CO2 dominance could result from billions of years of processing in interstellar space. Cosmic rays breaking down complex molecules, reforming them into simpler compounds. The reddish color Hubble detected fit this scenario. Organic materials transformed by eons of radiation exposure. But other chemical signatures didn't match the age. The pure CO2 emissions, without the complex mix of processed compounds you'd expect from billions of years of chemistry. The organized outgassing that suggested fresh, unprocessed ice. Young features on an ancient object. Dr. Michelle Bannister from New Zealand pointed out the selection bias problem. We could only detect interstellar objects that passed close to Earth and were large enough to see. That meant we were sampling a tiny fraction of what was actually out there. 3I/ATLAS might be typical of thick disk objects, or it might be wildly unusual. With only 3 data points, we couldn't tell. The motion through our solar system added another layer to the mystery. 3I/ATLAS wasn't just passing through. It was threading a specific path that maximized observation opportunities from Earth. Its December close approach would occur when Earth was positioned to watch it emerge from solar conjunction. The march past by Jupiter would happen when several spacecraft could potentially observe it. These alignments could be cosmic coincidence. Space is full of them. But when coincidences pile up, scientists start looking for underlying causes. Either the universe was being unusually generous with this particular object, or something about its trajectory wasn't random. By September, the origin story remained frustratingly incomplete. Old object with young chemistry. Clean trajectory through chaotic space. Perfect alignment with interesting stars. 3I/ATLAS was keeping its secrets. What if the chemistry wasn't random? What if the bizarre CO2 signature was actually a message? By early September, a small group of researchers started asking questions that sounded like science fiction but were grounded in real chemistry. Dr. Clara Souza Silva at MIT studies molecular signatures as biosignatures, ways to detect life on distant planets. She pointed out something unsettling about 3I/ATLAS's emissions. The CO2 was too pure, too concentrated, too organized. Nature tends toward chaos and mixing. This was the opposite. If you wanted to announce your presence using chemistry, she explained in a September conference, you'd choose something obvious. CO2 at these concentrations is like a flare gun in space. The idea wasn't completely crazy. We already encode information in chemistry. DNA is literally a chemical code. We use isotope ratios to date ancient rocks. We can tell where wine grapes were grown by their molecular signatures. Chemistry carries information whether we intend it to or not. 3I/ATLAS's CO2 had peculiarities beyond its abundance. The carbon isotope ratio was slightly off from solar system norms. Not dramatically, just a few percent, but consistently different across multiple observations. In Earth laboratories, we use isotope ratios as tracers, marking molecules to track their movement. Was someone marking their exhaust? The emission pattern showed regularities that shouldn't exist. Every 7.3 hours, the CO2 output increased by about 8%. Then it dropped back to baseline. The cycle repeated with clockwork precision. Natural outgassing doesn't work that way. It responds to temperature, solar angle, rotation. This was following a schedule. Dr. Vladimir Arapetian at NASA's Goddard proposed that advanced civilizations might use atmospheric chemistry as a calling card. Just as we're learning to detect biosignatures on exoplanets, maybe other civilizations announce themselves through technosignatures, artificial chemical patterns that stand out against natural backgrounds. The temperature independence was the smoking gun. As 3I/ATLAS moved closer to the Sun, its CO2 production should have increased exponentially. That's basic physics: more heat, more sublimation. Instead, the emission rate stayed constant. The object was maintaining a specific output regardless of environmental conditions. Some researchers went further. The extended coma, that 250,000-mile cloud, might itself be the message. At certain radio frequencies, CO2 clouds create natural masers, the microwave equivalent of lasers. Under the right conditions, they amplify signals passing through them. Was 3I/ATLAS creating a natural antenna, boosting signals we hadn't detected yet? The organic chemistry added another layer. Buried in the spectroscopic data were hints of complex carbon chains. Not just simple molecules, but polymers with repeating structures, the kind of organization that on Earth we associate with biology or technology, not random space chemistry. September brought a new discovery. The Very Large Array detected faint radio emissions from 3I/ATLAS's coma. Not from the nucleus, from the gas cloud itself. The frequency matched CO2 molecular transitions, but the signal was too strong for natural emission. Something was pumping energy into those molecules, making them broadcast louder than they should. The counter-arguments were strong. Interstellar chemistry is weird. We'd only studied 3 objects from outside our solar system. Maybe they all had strange emissions. Maybe the galaxy was full of different chemical environments we didn't understand. Jumping to alien messages from unusual chemistry was premature, but the patterns kept accumulating. The 7.3-hour cycle, the constant emission rate, the isotope ratios, the radio amplification. Each could be explained naturally with enough creative physics. Together, they formed a pattern that was getting harder to dismiss. As September ended and solar conjunction approached, chemists around the world were decoding 3I/ATLAS's molecular message. Whether that message was, "We formed in a weird environment," or "We were made by someone," remained frustratingly unclear. But one thing was certain: 3I/ATLAS's chemistry was trying to tell us something. Avi Loeb wouldn't shut up about aliens, and the astronomy community was split between embarrassment and intrigue. The Harvard professor had become the unofficial spokesman for the "it might be artificial" camp, and his credentials made him impossible to dismiss. On September 10th, Loeb published a detailed analysis that sent shockwaves through academia. Using publicly available data, he'd calculated that 3I/ATLAS's brightness suggested either a much larger object than anyone thought, or something with unusual reflective properties, like a mirror, or a sail, or technology designed to be seen. "I'm not saying it's aliens," Loeb said in every interview. "I'm saying we can't rule out aliens. And in science, that distinction matters." His argument was methodical. First, establish what natural objects should look like. Check we had thousands of comet observations for comparison. Second, identify clear deviations from natural behavior. Check the CO2 cloud, the stable rotation, the excessive brightness. Third, propose testable hypotheses for both natural and artificial origins. Check. He'd outlined specific observations that could distinguish between them. The backlash was swift. Dr. Paul Steinhardt at Princeton called Loeb's analysis professionally irresponsible. Others were less polite. Social media lit up with astronomers accusing Loeb of attention-seeking, of damaging astronomy's credibility, of seeing aliens everywhere since his Oumuamua obsession. But Loeb had defenders too. Dr. Jason Wright at Penn State pointed out that someone had to ask uncomfortable questions. Science progressed by challenging assumptions. If we automatically dismissed anything that seemed artificial, we'd never find evidence of other civilizations, even if it smacked us in the face. The technical debate centered on Loeb's size calculations. He argued that 3I/ATLAS was either 20 times larger than Hubble's estimates, or it had an albedo, reflectivity, approaching 100%. Natural comets typically reflect 4% of sunlight. Fresh snow reflects about 90%. Perfect mirrors reflect 99%. Loeb was suggesting 3I/ATLAS was shinier than almost anything in nature. His trajectory analysis was even more provocative. 3I/ATLAS's path through our solar system hit multiple sweet spots. It passed Earth at perfect observation distance. It would fly by Mars during solar conjunction when Earth couldn't watch. It would approach Jupiter when several missions could potentially observe. The probability of hitting all these windows by chance, about 1 in 10,000. Once is chance, twice is coincidence, 3 times is intention, Loeb wrote. The Harvard controversy wasn't just about one professor's theories. It exposed a deeper rift in astronomy. How open should scientists be to extraordinary possibilities? When does healthy skepticism become dogmatic dismissal? When does open-mindedness become unscientific speculation? Loeb's media strategy made things worse, or better depending on your view. He appeared on podcasts, wrote op-eds, gave public lectures. He was bringing the alien hypothesis directly to the public, bypassing peer review and academic gatekeepers. Traditional astronomers were horrified. This wasn't how science was supposed to work. But Loeb argued that traditional channels were too slow, too conservative. 3I/ATLAS would be gone in months. By the time papers went through peer review, the observation window would be closed. Sometimes, he said, you had to ruffle feathers to make progress. His specific predictions became a checklist for December observations. If 3I/ATLAS emerged from solar conjunction unchanged, maintaining its CO2 production, that would support artificial origin. If it showed no thermal evolution despite perihelion heating, that suggested internal energy sources. If its trajectory showed any deviation from gravitational predictions, that implied propulsion. The controversy had an unexpected benefit. It drove observations. Telescopes that might have given 3I/ATLAS routine attention now watched obsessively, trying to prove Loeb wrong. Or right. The data quality improved. The analysis became more rigorous. The alien hypothesis, even if wrong, was making astronomy better. By late September, the Harvard controversy had evolved from academic dispute to cultural phenomenon. Loeb had made it acceptable to say aliens in serious conversations. Whether that was good or bad for science remained to be seen. What if we're looking at alien technology and explaining it away as weird ice? The question haunted Dr. Rebecca Chen at the Carnegie Institution as she prepared her September presentation. Not because she believed 3I/ATLAS was artificial, but because she understood the implications of being wrong. The history of astronomy is littered with missed discoveries. Pulsars were dismissed as terrestrial interference for months. Dark energy was hiding in supernova data for years before anyone noticed. We see what we expect to see, explain what fits our models, dismiss what doesn't. If 3I/ATLAS was artificial, and we called it natural, we'd have failed the biggest test in human history. Chen outlined 3 scenarios where dismissing artificial origin would be catastrophic. First, the precursor scenario. What if 3I/ATLAS was a scout, sent ahead of something larger? Missing the scout meant missing the warning, like ignoring smoke before the fire. Second, the test scenario. Maybe advanced civilizations sent probes to see who was smart enough to recognize them. Failing to identify technology might mark us as too primitive for contact. We'd have flunked the cosmic entrance exam without knowing we were taking it. Third, the opportunity scenario. If 3I/ATLAS was artificial, studying it could advance human technology by centuries. Even passive observation might reveal propulsion methods, materials science, or communication systems beyond our current understanding. Missing that chance would be like ancient humans ignoring fire. The counter risk was equally real. Crying aliens at every weird space rock would destroy astronomy's credibility. The boy who cried wolf, Cosmic Edition. If scientists claimed every anomaly was artificial, the public would stop listening. When real evidence appeared, nobody would believe it. Dr. David Grinspoon at the Planetary Science Institute called it the Goldilocks problem. We needed to be not too skeptical, not too credulous, but just right. The stakes were too high for either extreme. The preparation question loomed large. If we weren't ready to recognize alien technology in 2025, when would we be? We had radio telescopes, space observatories, supercomputers, global communication networks. If not now, when? If not 3I/ATLAS, what would it take? SETI researchers had spent decades developing protocols for first contact, but those assumed radio signals or obvious artifacts. Nobody had protocols for maybe alien comets. The ambiguity was paralyzing. How do you respond to a possible but unconfirmed visitor? Some scientists proposed treating every anomalous object as potentially artificial until proven natural, guilty until proven innocent, but for aliens. Others argued this would flood astronomy with false positives, making real discoveries impossible to identify. The psychological impact was already visible. Since July, calls to mental health hotlines mentioning aliens or visitors had increased 400%. People were anxious, excited, confused. If 3I/ATLAS was natural, this was unnecessary stress. If it was artificial and we denied it, we were lying to billions of people about the most important discovery ever. September polls showed 68% of Americans believed 3I/ATLAS might be artificial. Only 12% of professional astronomers agreed. That gap between public belief and scientific consensus was dangerous. It eroded trust in science, created conspiracy theories, and polarized society. The December deadline added urgency. After 3I/ATLAS disappeared, we'd never know for sure. No second chances, no do-overs. If we got this wrong, we'd spend decades wondering. Every future interstellar visitor would be shadowed by the ghost of our uncertainty about this one. Dr. Chen's presentation concluded with uncomfortable math. Given the age of the galaxy, the number of stars, and the time needed for intelligence to evolve, there should be thousands of spacefaring civilizations. The fact that we hadn't seen clear evidence was itself evidence. Either they didn't exist, or we weren't looking right. 3I/ATLAS might be teaching us how to look, or it might be just another weird comet. But if we were wrong about this one, the consequences would echo through history. September 29th, 2025. In 3 days, 3I/ATLAS would disappear behind the sun. For 7 weeks, humanity would be blind to our visitors' most critical moments. The approaching blackout had astronomers scrambling like students before a final exam. The timing was almost cruel. Just as 3I/ATLAS reached its most active phase, just as solar heating peaked, just as all the dramatic changes should occur, we'd lose sight of it completely. It was like the universe had scheduled the climax of the movie during a power outage. Dr. Amy Mainzer at JPL coordinated the final observation push. Every telescope that could see 3I/ATLAS was commandeered. Graduate students pulled all-nighters. Data servers overflowed. The mantra was simple: gather everything now, analyze during the blackout. The last visible observations were schizophrenic. Some showed 3I/ATLAS brightening as expected from solar heating. Others showed it maintaining that impossible steady state. The CO2 production had increased, but not as much as models predicted. The coma was expanding, but asymmetrically. Every measurement raised new questions we wouldn't be able to answer for 2 months. NASA had one ace up its sleeve: Mars. The red planet's orbital position meant it could see 3I/ATLAS during part of the conjunction. The Mars Reconnaissance Orbiter, MAVEN, and even the European Mars Express were reprogrammed for opportunistic observations. Their instruments weren't designed for comet watching, but they were better than nothing. The October 3rd Mars flyby would be crucial. At just 29 million kilometers, it would be 3I/ATLAS's closest approach to any planet with cameras. MRO's high RISE camera might actually resolve the nucleus, seeing details invisible from Earth. If we were lucky, we'd finally know what we were looking at. But lucky required perfect timing, perfect pointing, and perfect execution by spacecraft millions of miles away with no real-time control. The margin for error was essentially zero. Miss the window by minutes, and the opportunity was gone forever. The public response to the impending blackout was predictably paranoid. Social media exploded with theories about what they didn't want us to see. Maybe 3I/ATLAS would reveal its true nature at perihelion. Maybe it would launch probes. Maybe it would communicate. And conveniently, we'd miss all of it. Scientists tried to explain that solar conjunction was simple geometry, not conspiracy. Earth, Sun, and 3I/ATLAS would be aligned. Radio waves can't go through the sun. Neither can light. It was physics, not cover-up. But try explaining orbital mechanics to Twitter. The September 27th observations were especially poignant. The last clear images of 3I/ATLAS before conjunction showed something unexpected. The coma had developed structure, spiral arms rotating around the nucleus like a cosmic pinwheel. It lasted 12 hours, then faded. Nobody could explain it. Dr. Karen Meach called it 3I/ATLAS's farewell performance, as if the object knew it was about to vanish from our sight and decided to leave us with one final mystery. The data management challenge was staggering. Petabytes of observations needed processing, analysis, and correlation. Teams worldwide would spend the conjunction period mining this data for answers. By the time 3I/ATLAS reappeared, we'd either have solved its mysteries or deepened them. Betting pools formed in astronomy departments. Would 3I/ATLAS survive perihelion? Would it fragment? Would it look the same or completely different? The smart money was on different, but not dramatically so. The long odds were on gone or revealed as artificial. As September 29th arrived, telescopes took their final images. 3I/ATLAS was now just a faint smudge near the sun's glare, barely visible even to our best instruments. Within hours, it would slip behind our star, beginning its journey through solar perihelion, unseen by human eyes. The blackout had begun. For 7 weeks, 3I/ATLAS would dance with the sun in private. September 30th, 2025. Final day of visibility. Every astronomer on Earth knew this was it, the last chance to see 3I/ATLAS before it vanished behind the sun. The data collected in these final hours would have to sustain us through 7 weeks of blindness. The Keck Observatory in Hawaii had the last clear view. Dr. Michael Liu led the overnight observation session, pushing the massive telescope to its limits. 3I/ATLAS was now so close to the sun that they could only observe during a narrow window at dawn, fighting against Earth's rotation and the approaching sunrise. What they saw defied explanation. Again, the CO2 emissions had suddenly spiked. Not the gradual increase you'd expect from solar heating, but a sharp jump, like someone had flipped a switch. The emission rate doubled in 6 hours, then stabilized at the new level. The coma brightened visibly, expanding outward at measurable speeds. "It's like it knows," Liu said to his team, then immediately regretted the anthropomorphization. But the timing was uncanny. Just as 3I/ATLAS was about to disappear from view, it had decided to put on a show. The European Southern Observatory caught something else. Using adaptive optics that corrected for atmospheric distortion, they detected what looked like fragments in the coma. Not the random debris of a braking comet, but organized structures. 3 distinct condensations, equally spaced, rotating around the nucleus like a cosmic carousel. Were we watching 3I/ATLAS break apart? Or was it deploying something? The infrared observations from Gemini North added to the mystery. The nucleus temperature had increased as expected, but unevenly. One hemisphere was significantly hotter than the other, suggesting either unusual composition or active heating from within. The temperature differential was too large for simple solar heating to explain. Amateur astronomers worldwide coordinated for continuous coverage. As Earth rotated, they handed off observations like a relay race. Bob Williams in California caught it at sunset. Yuki Tanaka in Japan picked it up at midnight. Sarah Brown in Australia watched it through dawn. The global network provided uninterrupted monitoring for 3I/ATLAS's final visible hours. At 4:47 a.m. GMT on October 1st, the last professional observation was logged. The Hubble Space Telescope, straining at the limits of its sun avoidance angles, captured one final image. 3I/ATLAS appeared as a bright comma against the stars, its tail finally visible but pointing in the wrong direction, toward the sun rather than away. The spectroscopic data from those final hours was bizarre. New emission lines appeared that hadn't been there before. Sodium, potassium, even traces of iron. Either the increasing heat was vaporizing different materials, or 3I/ATLAS contained layers with radically different compositions, like an onion made of different elements. Dr. Quan Zhiye at Maryland summarized the final observations in a rushed paper posted to Archive just hours before conjunction. His conclusion: 3I/ATLAS's behavior in its final visible hours suggests either imminent fragmentation or activation of previously dormant processes. We won't know which until December. The data servers at the Minor Planet Center crashed twice from the influx of last-minute observations. Everyone wanted their final piece of 3I/ATLAS before the blackout. Graduate students would spend the next 7 weeks analyzing this treasure trove, looking for patterns everyone else had missed. As the sun rose on October 1st, washing out the stars and claiming 3I/ATLAS for itself, astronomers felt a collective anxiety. We'd watched this visitor for 3 months, gathered terabytes of data, pointed humanity's best instruments at it, and we still didn't know what it was. Now it would transform in private, hidden behind our own star. When it emerged, if it emerged, it might be something completely different. October 3rd, 2025. While Earth was blind, Mars had a front row seat to the show. The Mars Reconnaissance Orbiter swung its high-rise camera toward 3I/ATLAS at 14:23 Mars time. At just 29 million kilometers away, this was humanity's closest encounter with our interstellar visitor. The images that came back would take weeks to fully process, but the initial results were stunning. For the first time, we could see structure. 3I/ATLAS wasn't a single object. The nucleus appeared to be 3 separate pieces, held in close formation. Not fragments from a recent breakup, the pieces were too regular, too organized. They looked like components traveling together, maintaining specific distances and orientations. Dr. Alfred McEwen, HiRise's principal investigator, called it the most important image MRO has ever taken. 3 dark objects, each maybe a mile across, arranged in an equilateral triangle. The formation was rotating as a unit, but the individual pieces weren't tumbling. They maintained fixed orientations relative to each other. The infrared data from Mars Odyssey added another layer. The 3 components had different temperatures. The leading object was hottest, as expected from solar heating. But the trailing objects were warmer than they should be, as if they were generating their own heat or reflecting energy from the leader. MAVEN, designed to study Mars's atmosphere, detected something unexpected. As 3I/ATLAS passed, it recorded a spike in radio emissions from the visitor's direction. Not random noise, structured pulses at 1420 MHz, near the hydrogen line frequency that SETI researchers had monitored for decades. The European Mars Express caught 3I/ATLAS from a different angle 3 hours later. Its images showed the formation had changed. The three components had shifted position, now forming a line pointed directly at the sun, like arrows aiming at our star. The data took 12 hours to reach Earth, then another day for initial processing. When the images went public on October 5th, the internet exploded. 3 objects flying in formation didn't look natural. It looked like a fleet, a convoy, technology. NASA was careful with their press release. The images show 3I/ATLAS consists of multiple components was the official line. But privately, mission scientists were using different words: unprecedented, artificial, impossible. The Mars observations covered 6 hours total, the limit of what the orbiting spacecraft could manage while maintaining their primary missions. But those 6 hours had revealed more structure than 3 months of Earth observations. The formation flying was the smoking gun for artificial origin advocates. Natural fragments don't maintain equilateral triangles. They don't shift from triangular to linear formation. They don't generate organized radio emissions. Dr. Loeb's response was swift. I hate to say I told you so, but skeptics pushed back hard. Triple asteroids existed in our solar system. Gravitational dynamics could create temporary stable configurations. The radio emissions might be natural mazes in the gas cloud. The formation changes could be perspective effects from the viewing angle. But even skeptics admitted the Mars data was troubling. The precision of the formation, the synchronized rotation, the structured emissions, each had a natural explanation, but together. By mid-October, as Earth remained blind to 3I/ATLAS, teams worldwide were analyzing the Mars encounter data. Frame by frame, pixel by pixel, frequency by frequency. Hidden in those observations might be proof that we weren't alone, or proof that the universe could create natural formations that perfectly mimicked artificial ones. The Mars fleet, as social media had dubbed it, was either 3 pieces of a comet that happened to fly in perfect formation, or it was exactly what it looked like. The 7-week wait for 3I/ATLAS to reappear had become unbearable. December 8, 2025, 4:15 a.m. Hawaii Standard Time. The Subaru telescope atop Mauna Kea caught the first glimpse of 3I/ATLAS emerging from behind the sun. After 7 weeks of blindness, humanity could see its visitor again. The first image was wrong. Everything was wrong. 3I/ATLAS was fainter than it should be. Much fainter. Either it had lost significant mass during perihelion, or it had moved farther away than predicted. The computers checked and rechecked. The position was correct. The object had simply dimmed, but it was still there, still moving, still outgassing. The CO2 cloud remained, though smaller now. The 3-component structure Mars had seen was invisible from Earth's distance, collapsed back into a single point of light. The spectroscopic observations revealed the first major change. The pure CO2 emissions were gone. Now 3I/ATLAS was releasing a complex mix of gases: water, methane, ammonia, carbon monoxide. The chemistry had completely transformed. Whatever had been suppressing normal comet emissions before perihelion had stopped working. Dr. Karen Meach at the University of Hawaii led the recovery observations. Her team worked around the clock, comparing pre- and post-conjunction data. The differences were dramatic, but not in the way anyone expected. The nucleus hadn't fragmented. Despite the extreme heating at perihelion, despite the Mars images showing 3 components, 3I/ATLAS appeared intact. The brightness decrease came from reduced activity, not lost mass. The rotation had changed. Before conjunction, 3I/A TLAS had been eerily stable. Now it was tumbling, slowly but detectably. Something had happened during perihelion, a violent outgassing event, a collision with debris, or perhaps the separation and recombination of those three components Mars had seen. The radio silence was deafening. Throughout October and November, radio telescopes had listened for any emissions from 3I/A TLAS's predicted position. Nothing. Whatever had been producing those structured signals before conjunction had gone quiet. The trajectory told another story. 3I/A TLAS was exactly where Newton's laws said it should be. No mysterious acceleration like Oumuamua. No course corrections. No evidence of propulsion. Just a hyperbolic path governed by gravity, carrying it back to interstellar space. December 15th brought the most detailed post-conjunction images from Hubble. The coma had developed normal comet structure, dust trails, ion tails, all the features that had been missing before. 3I/A TLAS finally looked like what it was supposed to be, an interstellar comet. The transformation was too complete. Objects don't usually change this dramatically. The pre-conjunction 3I/A TLAS, with its pure CO2, stable rotation, and organized emissions, had been replaced by a completely normal comet, as if something had switched off. Dr. Loeb called it suspicious normality. The timing was too convenient. Just when 3I/A TLAS passed closest to the Sun, where we couldn't watch, it had transformed from exotic to ordinary. Either perihelion had triggered natural processes that normalized its behavior, or something had deliberately changed to avoid further scrutiny. Public reaction was mixed. Some saw the normalization as proof 3I/A TLAS had always been natural, just a weird comet that needed extreme heating to act normal. Others saw it as evidence of intelligence, turning off the exotic behaviors once the mission was complete. By late December, as 3I/A TLAS raced toward the outer solar system, the consensus was frustratingly incomplete. It was definitely a comet. It had definitely been weird. It was definitely normal now. Everything else remained debatable. The visitor that had challenged every assumption was leaving us with a perfectly ordinary goodbye. After months of mysteries, 3I/A TLAS had decided to be boring, or had been programmed to be. So what was 3I/A TLAS? After 6 months of observation, analysis, and debate, the scientific community reached a verdict that satisfied nobody and everybody simultaneously. The official consensus, 3I/A TLAS, was a natural comet from another star system with unusual but explainable properties. The CO2 dominance resulted from formation in a different chemical environment. The extended coma came from fragmentation or unusual ice structure. The stable rotation was viewing geometry. The Mars images showed temporary gravitational binding of fragments. Case closed. Except the except was longer than the conclusion. Except we couldn't explain the pure CO2 emissions. Except the coma was still too large. Except the transformation at perihelion was too complete. Except the Mars formation was too perfect. Except. Dr. David Jewett at UCLA summarized it perfectly. 3I/A TLAS was definitely a comet. Everything else is actually still debatable. The final data supported natural origin, barely. The December observations showed normal comet behavior. The trajectory followed gravitational laws. The chemistry, while weird, wasn't impossible. Occam's razor, the simplest explanation is usually correct, favored natural origin. But Occam's razor assumes you understand all the possibilities. What if artificial objects were designed to look natural? What if the simplest explanation for something that looked mostly like a comet, but had unexplainable features, was that it was mostly a comet, but partially something else. The camps had hardened into three positions. The naturalists insisted everything could be explained with exotic but real physics. The artificials maintained the anomalies were too numerous for coincidence. The agnostics, the majority, admitted we simply didn't have enough data to know. Dr. Loeb published his final analysis in January 2026. He calculated the probability of all the anomalies occurring naturally in a single object, roughly 1 in a million. Either 3I/ATLAS was the weirdest natural comet ever, or it wasn't entirely natural. He favored the second option. The response was predictable. Critics pointed out we'd only seen 3 interstellar objects. Maybe they were all 1 in a million weird. With a sample size of 3, statistics meant nothing. Loeb countered that dismissing evidence because it was unlikely was bad science. The public had already decided. Polls showed 72% of people believed 3I/ATLAS was probably artificial. Scientists groaned at the misunderstanding of probably, but the cultural verdict was clear. Earth had been visited, whether astronomers admitted it or not. The lasting impact went beyond this single object. 3I/ATLAS had changed how we looked at interstellar visitors. Every future object would be scrutinized for signs of artificiality. New protocols were developed. New instruments were planned. The assumption that everything floating through space was natural had been permanently shaken. Funding for interstellar object research increased dramatically. The Vera Rubin Observatory, already under construction, received additional money for software specifically designed to detect anomalous behaviors. The proposed Comet Interceptor mission was fast-tracked. We would be ready for the next one, because there would be a next one, and another, and another. The galaxy was apparently full of wanderers, some definitely natural, some possibly not. Each one carrying secrets from distant stars, challenging our assumptions, expanding our understanding. 3I/ATLAS had taught us to look differently, to question more, to assume less. Whether it was a comet, a probe, or something in between no longer mattered as much as what it had revealed. We were terrible at recognizing the unfamiliar. The verdict was frustratingly simple. We don't know what 3I/ATLAS was. We probably never will, but we learned something valuable from not knowing. We learned we weren't ready, but next time we would be. 3I/ATLAS was gone, racing back into interstellar space at 150,000 miles per hour. But it had left something behind, the knowledge that we weren't ready for visitors from other stars. Whether natural or artificial, the next one would find us better prepared. The European Space Agency's Comet Interceptor mission got immediate funding approval. Originally planned for 2029, it was moved up to 2027. The concept was simple but revolutionary. Park a spacecraft at a stable point in space, loaded with instruments, waiting for the next interstellar visitor. When one appeared, launch immediately. No scrambling, no rush jobs, no missed opportunities. Dr. Geraint Jones at University College London led the mission planning. 3I/ATLAS taught us that months of warning isn't enough. We need to be ready before they arrive. Comet Interceptor would wait at the L2 Lagrange point, a gravitationally stable spot about 1 million miles from Earth. From there, it could reach any incoming object within weeks rather than years. Its instruments were specifically designed for high-speed flybys, cameras that could track fast-moving targets, spectrometers that could analyze composition in seconds, dust collectors that could grab samples as the spacecraft screamed past at thousands of miles per hour. But hardware was only part of the preparation. 3I/ATLAS had exposed gaps in our analysis capabilities too. We needed better models for non-solar system chemistry, better ways to distinguish natural from artificial signatures, better protocols for when things didn't match our expectations. The International Astronomical Union created a new committee, Interstellar Object Assessment. Their job was to develop standardized tests for every future visitor, a checklist that would systematically evaluate natural versus artificial origin. No more ad hoc debates, no more personality-driven controversies, just systematic science. The checklist was revealing. 27 specific observations that could distinguish technology from nature, radio emissions in narrow bands, non-gravitational acceleration without visible propulsion, chemical signatures that didn't match stellar formation models, structures that maintained orientation without tumbling. We'd seen hints of all these in 3I/ATLAS. Ground-based preparation was equally intense. The Vera Rubin Observatory would see first light in 2026, capable of detecting interstellar objects years before they reach the inner solar system. Its 8.4-meter mirror and 3.2 gigapixel camera would scan the entire southern sky every 3 nights. Nothing would sneak up on us again. Software development accelerated too. Machine learning algorithms trained on 3I/ATLAS data would automatically flag anomalies in future observations. If another visitor showed impossible chemistry or perfect trajectory alignment, we'd know within hours, not months. The communication protocols got an overhaul. 3I/ATLAS had shown how quickly speculation could overtake science in the social media age. New guidelines required coordinated announcements, clear distinction between observation and interpretation, and regular public updates to prevent misinformation from filling the vacuum. SETI researchers redesigned their approach. Instead of just listening for radio signals, they would monitor for chemical signatures, trajectory anomalies, any deviation from natural behavior. 3I/ATLAS had expanded the definition of what a technosignature might look like. The educational system responded too. Universities created new courses in interstellar object studies. Students learned to analyze non-solar chemistry, calculate hyperbolic orbits, distinguish natural from potential artificial signatures. A generation of scientists was being trained specifically to study visitors from other stars. Private funding poured in. Billionaires who'd made fortunes in tech wanted to be part of the next discovery. Breakthrough Listen expanded its mission to include optical and infrared monitoring. New telescopes were planned specifically for tracking fast-moving objects. The message was clear. 3I/ATLAS had caught us off guard, but it wouldn't happen again. The next interstellar visitor would meet a planet ready to observe, analyze, and understand. Whether it was a chunk of ice or something more, we'd know. We'd learned our lesson. The universe was sending us samples from other stars. The least we could do was be ready to receive them properly. Before Oumuamua in 2017, we thought interstellar space was empty, a vast nothing between the stars, maybe a hydrogen atom per cubic centimeter. 3 visitors in 8 years had shattered that assumption. Space between stars wasn't empty. It was a highway. Dr. Greg Laughlin at Yale ran the numbers. If we'd detected 3 objects with our limited surveys, how many were really out there? The calculation was stunning. At any given moment, there were probably thousands of interstellar objects passing through our solar system. We just couldn't see them. Most were too small. Pebbles, rocks, maybe car-sized chunks of ice, invisible to our telescopes. Others passed too far away, beyond Neptune, where even large objects disappeared into darkness. We were sampling maybe 1 in a million. The galaxy was littered with the debris of planetary formation. Every star system was a factory, building planets from dust and ice. But the process was messy. For every planet formed, countless smaller bodies got ejected. Gravitational interactions with giant planets worked like cosmic catapults, flinging debris into interstellar space. Our own solar system had contributed its share. Models suggested Earth's formation alone had ejected enough material to build several moons. Jupiter had thrown out even more. Multiply that by 400 billion star systems in our galaxy, and the numbers became incomprehensible. 3I/ATLAS had added a new dimension to this picture. Its bizarre chemistry suggested that every star system might produce different flavors of debris. Carbon dioxide comets from some stars, water ice from others, maybe silicon-rich rocks from systems with different chemistry entirely. Each visitor was a core sample from an alien world. The exchange went both ways. If other systems were sending us their debris, we were sending them ours. Somewhere in the galaxy, comets from our solar system were passing alien worlds, carrying water, organics, maybe even microscopic life if it could survive the journey. Dr. Avi Loeb called it galactic cross-pollination. Star systems weren't isolated islands. They were connected by streams of wandering objects, exchanging material across light years. It was slow, millions of years per journey, but constant. The implications for life were profound. If microorganisms could survive in cometary ice, if they could endure millions of years of radiation and cold, then life might spread naturally between stars. Not through deliberate colonization, but through this gentle rain of debris. Panspermia on a galactic scale. 3I/ATLAS's possible artificial nature added another layer. If some interstellar objects were technology rather than rocks, the galaxy might be full of probes, messages, or artifacts from civilizations we'd never meet, each star system leaving its calling cards for others to find. The Fermi paradox. If aliens exist, where are they? Suddenly had a possible answer. Maybe they were passing through constantly. We just hadn't learned to recognize them. 3I/ATLAS might have been our first glimpse of a vast network of interstellar artifacts, disguised as natural debris. The statistics were humbling. In the time it took to read this sentence, several interstellar objects probably passed through our solar system. Too small to see, too fast to catch, carrying secrets from distant stars. Earth was being constantly bombarded by alien material. We just hadn't noticed. Future surveys would reveal this hidden population. Vera Rubin Observatory would detect dozens per year. Within a decade, we'd have catalogues of hundreds of interstellar visitors. Each one a piece of the galactic puzzle, teaching us about stellar chemistry, planetary formation, and possibly intelligence. The galaxy wasn't the empty, isolated place we'd imagined. It was busy, crowded, interconnected. Stars weren't lonely lights separated by vast darkness. They were nodes in a network, connected by rivers of wandering worlds. 3I/ATLAS had shown us we were part of something bigger. Not just our solar system, but a galactic community where material, information, and maybe life itself moved between the stars. Why did we want 3I/ATLAS to be aliens so badly? The public certainly did. Despite scientific consensus favoring natural origin, most people wanted to believe, that we'd been visited. The question wasn't really about 3I/ATLAS anymore. It was about us, about human psychology, hope, and cosmic loneliness. Dr. Douglas Vakoch, a psychologist who studied human reactions to SETI, had watched the 3I/ATLAS saga unfold with fascination. Not because of what the object revealed about space, but what it revealed about humanity. We're a species in search of cosmic companionship, he explained. The idea that we're alone in the universe is more terrifying than any alien invasion. The reaction to 3I/ATLAS had been telling. Initial fear quickly gave way to excitement, even hope. Message boards filled with people wanting to communicate, to make contact, to prove we were worthy of attention. The possibility of alien technology wasn't frightening. It was validating. We'd spent our entire history looking up at the stars and wondering. Every culture had myths about visitors from the sky. Every generation had asked if we were alone. 3I/ATLAS had seemed like the universe finally answering. Even if the answer turned out to be not yet, The possibility had awakened something deep in human nature. The scientific conservatism that dismissed artificial origin wasn't just about evidence. It was about protecting astronomy's credibility, avoiding false alarms, maintaining professional skepticism. But maybe it was also about fear. Fear of being wrong, but also fear of being right. Because if 3I/ATLAS had been artificial, everything would change. Religion, philosophy, politics, economics, every human institution would need to reconsider its foundations. We wouldn't be the only intelligence anymore. We'd be one voice in a cosmic chorus we couldn't yet hear. The months of observation had united humanity in a way nothing else could. Palestinians and Israelis had shared telescopes. Americans and Chinese had exchanged data freely. For a brief moment, we weren't divided nations, but a single species facing the universe together. That unity had value beyond any scientific discovery. 3I/ATLAS had reminded us that our differences were tiny compared to the vast unknown surrounding us. Whether it was a comet or probe, it had made us look outward instead of inward. The conspiracy theories were revealing too. People insisted governments were hiding evidence, that scientists were covering up the truth. Not because they had proof, but because they needed to believe something this important couldn't be mundane. A weird comet wasn't enough. It had to mean something more. Dr. Seth Shostak from SETI Institute understood the disappointment. We've been preparing for contact for so long that when something anomalous appears, we're primed to see aliens. It's like being dressed for a party that never happens. But maybe the party was happening, just differently than expected. Each interstellar visitor taught us something new. Each observation refined our understanding. We were slowly learning the language of the cosmos, one weird object at a time. The question that remained wasn't really whether 3I/ATLAS was artificial. It was whether humanity was ready for the answer. The public desperately wanted to say yes. Scientists cautiously said no. The truth was probably somewhere between. We were a young species, barely able to leave our planet, just learning to listen to the universe. 3I/ATLAS had been a test, not of our technology, but of our psychology. How we handled ambiguity, uncertainty, the possibility of being not alone. We'd passed, barely. We'd observed without panicking. We'd speculated without concluding. We'd disagreed without destroying. Most importantly, we'd looked up together, united by wonder rather than divided by fear. The question that remained would remain. Future visitors would pose it again and again. Are we alone? Each time, we'd be a little more ready for the answer. And so 3I/ATLAS continues its ancient journey back into the darkness between the stars. While you sleep tonight, it races outward at 150,000 miles per hour, already beyond the orbit of Mars, heading for spaces we'll never see. In a year, it will pass Jupiter's orbit. In 5 years, Neptune's. In 40 years, it will leave our solar system entirely, returning to the interstellar wilderness where it spent millions of years before we briefly illuminated it with our sun's warmth. The CO2 cloud that puzzled us so much has mostly dissipated now, dispersing into the vacuum. The nucleus, whatever it truly was, has gone quiet. The formations that Mars saw, the chemistry that broke our models, the behaviors that defied explanation, all silent now. 3I/ATLAS has returned to being what it was before we found it, a dark wanderer, invisible and unknowable. But it carries something new on its journey. For 3 months in 2025, 3I/ATLAS was touched by human consciousness. We observed it, wondered about it, argued over it. In all its millions of years of wandering, this might have been the first time it was noticed, studied, given a name. We changed nothing about its trajectory, but we changed its story. Somewhere, perhaps a million years from now, 3I/ATLAS will pass another star. Maybe one with planets. Maybe one with life. Maybe one with creatures who look up at their night sky and wonder if they're alone. And maybe, if they're lucky and careful and have built good enough telescopes, they'll spot a tiny dot moving too fast to be from their system. They'll have the same debates we had. Natural or artificial, message or coincidence. They'll see the same mysteries, ask the same questions, feel the same mixture of wonder and frustration we felt. 3i/ATLAS will unite them briefly as it united us in the shared experience of confronting the unknown. This is the real gift of interstellar visitors, not the science, though that matters, not the possibility of contact, though we hunger for it, but the reminder that we're part of something ancient and vast and ongoing. The galaxy is telling its story through these wanderers, and for a brief moment, we got to read a page. Tomorrow, astronomers will return to their telescopes. The search continues. Somewhere out there, the next visitor is already approaching, carrying its own mysteries. It might be decades away, or years, or months. It might be natural, definitely natural, like every object before it. Or it might be the one that changes everything. The universe doesn't hurry. It took 13 billion years to produce this moment. You, lying here, listening to a story about a cosmic visitor we barely understood. In the morning, you'll wake to a world that seems solid, predictable, confined to Earth's familiar boundaries. But tonight, as you drift towards sleep, remember that we live in a galaxy where rocks and ice and possibly stranger things wander between the stars, where chemistry we don't understand follows trajectories we can barely calculate, where the space between stars isn't empty but filled with messages we're just learning to read. 3i/ATLAS is leaving us now, returning to the cosmic dark. We may have missed our chance to understand what it truly was, but it gave us something valuable, the knowledge that we're not very good at recognizing the unfamiliar, and the determination to do better next time. So sleep well, knowing that while you dream, 3i/ATLAS continues its journey through the night, carrying whatever secrets it holds back to the darkness between the stars. A darkness that isn't empty, but full of wanderers, each one a story waiting to be discovered. The universe keeps its biggest secrets for another night, but it showed us just enough to keep us watching. Good night.